Problem set 3 involves projectile motion. It's also going to review facts revolving around linear motion with some information about forces, because it presupposes that we did chapter 3, which is actually Newton's first law of motion. However, we are going to concentrate on some of the vector problems that we've done before and also the projectile problems. Here are some basic equations that you should know. And it'll be a review from the past chapter. dy of t is dy equals v naught t plus 1/2 at squared. Vf of d is vf squared vf squared equals v naught squared plus 2ad. Next is going to be vf of t, and we know that vf equals v naught plus at. In the case of free fall motion, v naught is 0, a is g, so vf equals gt. Now, there are going to be some basic equations for solving projectile motion problems. The first one is going to be Vx equals V naught cosine theta. Number 2 is Vy equals V naught sine theta. You should be used to these right away. If you're given Vy and Vx, and you know that tangent theta equals Vy over Vx, and you could determine the angle by arc tangent Vy over Vx equals theta. We know that if you know Vx and Vy, V naught would be the square root of the sum of the squares, Vx squared plus Vy squared. As spoken before, if V naught is 0 from rest, Vy equals gty. Rearranging that equation, you know that ty equals Vy over g. Next, we know that dy equals V naught ty plus 1/2 g ty squared. And dy equals 5 ty squared, that's from rest. V naught t drops out because it's from rest. And then rearranging that formula, you get ty equals root 2 dy over g. And then we know that vx equals dx over ty. Remember, ty equals 2, tx equals 2 ty, dx equals vx tx, and wait for it, tx equals ty in type 1. Remember, it's type 1. In type 2, tx equals 2 ty. I may have misspoken before, but that clears it up. Tx equals ty, tx equals 2 ty. Emanuele Zucchini, the famous human cannonball, was fired out of a cannon with a speed of 24 meters per second at an angle of 40 degrees to the horizontal. If he landed in a net 56.6 meters away at the same height from which he was fired, how long was Zucchini in the air? Well, here's the setup. We know that he's going to be landing 56.6 meters away. He's going to be 24 meters per second is going to be his initial velocity, v naught. The angle is going to be 40 degrees. Now, if he fired himself at 45 degrees, he would get the farthest distance given that velocity. So here's the trajectory, and we want to answer the question, how long was zucchini in the air. But what I'd like to do is, I'd like to do the whole problem from beginning to end. I want to find ty, tx, dy, and dx, vx, vy, etc. So here is the first. Here is vy and vx. So vy is going to be 15.4 meters per second, and Vx is going to be 18.4 meters per second. So what I'll do is I'm going to start this to go a little bit faster through the problem, maybe 5 to 7 seconds. So I'll be right back. I'm going to take a quick break. Okay, this is going to be set up to various small problems. I'm going to add little things, so it's going to be many frames. Here I've added the vectors. Now I want to concentrate on 15.4 meters per second. These slides are going to be 7 seconds each. I want to find ty, and I'm going to simply work out the derivation for the ty equation given the type 2 projectile motion. We know that VF here is going to be 0, so that term cancels. We see that negative g because it's going up. So now it's going to be negative Vy equals negative GT. I'm going to be able to divide through by -1, and then I'm going to be solving for the short form equation. That's Vy equals GT. I could have used that equation to begin with, but I wanted to derive the appropriate equation, which is Ty equals Vy over G. Plugging in, we get the appropriate answer, 1.54 seconds. 15.4 divided by 10 is 1.54. And we have to recognize that Tx is twice Ty, so 1.54 times 2, and that's going to be 3.08 seconds. 3.08 seconds. Now, the next thing I want to do is I want to derive the equation for dy, given the initial velocity, 15.4 meters per second. We see that it's going to be negative g because it's going to be going vertical. It's going to be going up, so it's going to be rising. So g is negative 10 meters per second squared. Simplifying slightly, we know that 1/2 of g is going to be 5, so it'll be Vy Ty equal minus 5 Ty squared. So that's the final equation for launching in a vertical direction, kind of a little bit of a short form there. And I will plug in the appropriate values. I get 15.4 meters per second times 1.54 minus 5 times 1.54 squared. And then that's going to be 11.9. Make sure you can get that yourself. Put everything on pause and try to do dx yourself. Try to do dx by yourself. Here's the equation. Dx equals Vx Tx. We know that the Vx is 15.4 meters per second. Tx is 3.08 seconds. Plugging into the equation, 15.4 times 3.08, and your answer, the seconds will cancel. You'll be left with meters, and you'll be going downrange 56.6 meters. 56.6 meters. I'm going to take a break. You'll never know I was gone. Now, the next problem, in her physics lab, Melanie rolls a 10-gram marble down a ramp and off the table with a horizontal velocity of 1.2 meters per second. The marble falls in a cup placed 0.51 meters from the table's edge. How high is the table? Well, let's first come up with a simplified version to measure dy from an initial velocity of 0. So V naught t will cancel out. I'm left with 1/2 g ty squared. I'm going down, so g is positive. G is 10, so 1/2 of 10 is 5. So it's ultimately going to be dy equals 5 ty squared. We see here that the g is 10 meters per second, and 1/2 of 10 is 5. So I'm going to come up with a very convenient equation to measure dy. Any vertical distance from rest is going to be dy equals 5 ty squared. Now, setting up the problem, we know that dx is going to be 0.51 meters, and I have vx is 1.2 meters per second. So I have vx and tx. I can do tx. So how do I get tx? That's a very simple formula that I'm going to show you in a moment. Tx equals ty automatically. So then I simply say dy is 5 ty squared. So it's going to be dx over vx is going to be tx. So tx is 0.425. And so I know that that's ty. So ty is going to be 0.425 as well. Now determining dy is going to be 5 times 0.425 squared. Remember, tx and ty are the same for type 1 projectile motion. That concludes this particular problem. I'll take a break and then we'll do the next one. Next, on May 20th, 1999, 37-year-old Robbie Knievel, son of famed daredevil Evel Knievel, successfully jumped 69.5 meters over a Grand Canyon gorge. Assuming that he started and landed at the same level and was airborne for 3.66 seconds, what height from his starting point did this daredevil achieve? I remember Wide World of Sports growing up on, I don't even know if it's still on, it was on ABC as a kid. We used to watch Evel Knievel and his crazy motorcycle jumping over trucks and trailers and all kinds of strange things. It got more and more daring every show. He would always fall and break something. But anyway, be that as it may, this is the trajectory. And we know that he's going to go 69.5 meters. That's the distance across the canyon. We know that it's going to take him 3.66 seconds to get there. Thereby, we know what ty is going to be because it's half of tx. Remember the symmetry here. So ty equals 1/2 tx. So what is 1/2 of 3.66 seconds? And that's going to be 1.83 seconds. 1.83 seconds. And then we're going to plug that into the equation. dy equals 5 ty squared. Why that? Because if he's at the max and he fell, he would fall 1.31 seconds from rest. That's kind of a quick way of doing it. It's kind of a quick way of doing it, especially if you don't have the initial velocity. So the dy is indeed 16.7 meters. Be right back. This next one, Billy Joe stands on the Tallahatchie Bridge kicking stones into the water. A, if Billy Joe kicks a stone with a horizontal velocity of 3.5 meters per second and it lands in the water a horizontal distance of 5.4 meters from where Billy Joe is standing, what is the height of the bridge? And if the stone had been kicked harder, how would this affect the time it would take to fall? Vx and Vy are mutually independent. When I was a kid, there was a song by Bobby Gentry called Tallahatchie Bridge, and it was about Billy Joe McAllister. Anyway, kind of a sleepy song from the South, sounds like. Anyway, so we have a typical type 1 projectile motion problem, and here it is. So it's going to be kicked at a horizontal velocity of 3.5 meters per second, and it's going to go 5.4 meters. It's going to go 5.4 meters. And we can already answer B while we're waiting, and that is that B is, it doesn't matter how hard you kick it. It's going to fall at the same rate. Tx and Ty are equal, we know that. It's going to fall at the same rate. The horizontal velocity is independent of the vertical velocity. So it'll fall at the same rate. But what will happen to the distance? And I kind of answer that towards the end of the problem. So we know that Ty and Tx are equal. We know that Tx is going to be dx over Vx, 5.4 meters, divided by 3.5 meters per second. So that's going to be 1.54 seconds. We know that Ty is going to be the same time. So Ty is 1.54 seconds. So what do I do now? Now I know what Ty is, and I have a simplified equation falling from rest. So dy is going to be 11.9 meters. All right, it's going to be 5 times 1.54 seconds squared. And the answer will be 11.9 meters. Hope that's readable. It was written with the old style, equation writer. Okay, so that's the problem. And what we'll do is what happens to the distance? We're going to add to this problem a little bit. What happens to the distance that to the distance of the rock if he kicks it harder? Well, a harder kick the time will remain the same, but the distance will greatly increase proportionally to, how hard he hits it, how hard he additionally kicks the rock. But the Ty will be the same, but dx will be larger. I have a very lengthy answer for the next problem. Ferdinand the frog is hopping from lily pad to lily pad in search of a good fly for lunch. If the lily pads are 2.4 meters spaced apart and Ferdinand jumps with a speed of 5 meters per second, taking 0.6 seconds to go from lily pad to lily pad, at what angle must Ferdinand make each of his jumps? Each one's going to be 15 seconds, but it's going to go very quickly. I'm going to every single step. Well, here's the trajectory, beginning and end of Ferdinand the little frog. And you have a horizontal and vertical component that you can separate the yellow, the V0 component into. And here's some information. 5 meters per second, 2.4 meters is dx, 0.6 seconds is the total, 0.3 seconds therefore would be Ty, 6, V0 is 5. There's Ty is 0.3. This should be falling off the paper each step individually. So now I have V0, I have Ty, Tx, and dx. Now I am going to be able to do dy because I have 0.3 seconds. If something fell from rest, 0.3 seconds, it would fall down. I could do dy, but evidently I did vy first. Vy equals g ty, working backwards. Now I have vy. Vy is 3 meters per second. I can possibly do, I honestly don't remember what I'm going to do next. So let's see, I could do dy next. I could do vx next because I have dx and tx. And I know that vx is going to be 4 meters per second. That makes sense that I have a 3, 4, 5 triangle. I could have predicted that very, very easily. So now I want to know what the angle is. I guess I don't really care how high this is right now. Now I can use arctangent to get the angle. Here I am finding dy. dy is going to be, I could do 5 ty squared. I could pretend that there's something that's going to drop 0.3 seconds. And that's what I'm going to do. So if something dropped 0.3 seconds straight down, the dy would be 5 ty squared. I could do it that way. And so that's going to be 5 times 0.3 squared, 5 times 0.3 squared, 0.3 times 0.3 times 5. You could probably do that in your head. 0.45 meters, 0.45 meters. So now I have dy, vy, vx, v naught, dx, ty, tx. And all that's left now is the angle. So the angle will be the arctangent of 3/4, and that will finish it. So what is the arctangent of 3/4? So the arctangent of 0.75. So I'm going to plug in vy and vx next. By the way, you didn't really have to do dy or ty, but you like to try to do things completely to make sure everything makes sense anyway. So you're going to see that it's 37 degrees. 37 degrees is the angle. So that answers the question. 37 degrees. And to summarize it, the Ferdinand the Frog has to jump 93 degrees to go 2.4 meters. 2.4 meters. The next equation, the next problem is going to be about Superman. It's said to, taken from the theme song, leap tall building. It's playing, no, it's Superman. How high must a building be? How high of a building could Superman jump over if he wants to, at 60 meters per second, an angle of 75 degrees to the horizontal? So, Superman comic on television with George Reeves, a lot of fun. Well, that's the trajectory, that's dy. So I'm going to have to at least resolve the 75 degrees into vy, and then divide vy by 10 seconds, and then multiply that by, if it was from rest falling, 5.8 seconds, it would fall according to dy equals 1/2 gt squared. You could say 5 ty squared, and that would be 168.2 meters. 168.2 meters. The next problem is going to be a basketball problem. Mubarak jumps and shoots a field goal from the far end of the court into the basket at the other end, a distance of 27.6 meters. The ball is given an initial velocity of 17.1 meters per second at an angle of 40 degrees to the horizontal from a height of 2 meters above the ground. What is its velocity as it hits the basket 3 meters off the ground? So this is going to be a little bit different, a little confusing. I'll give you a hint. We're going to be using VF squared equals V naught squared plus 2AD as the solution, part of the solution to the problem. I have it there. VF squared equals V naught squared plus 2AD. Here I have the initial velocity, the angle, what it's going to land 1 meter off the ground. You should, the trigonometry should be second nature. Vy is 11 meters per second. Vx is 13 meters per second. Ty is going to be 1.1 seconds. Ty is going to be 1.1 seconds. This should become very second nature to you. So dy is going to be 5 ty squared, or 5 times 1.1 squared. So that's ty. And that's going to be 1.1 seconds, as I've said. And I need dy, which is 5 ty squared, or 6.05 meters. Here's how I do that. We're pretending something's falling from Dmax, from rest. And so you can use dy equals 5 ty squared. So that's pretty straightforward. And so that's the simplified equation. You can always cheat and say it's falling from rest at that height. And that's going to be 5 times 1.1 squared. As I've said, I'm kind of dragging this out a little bit. And it's going to be 6.05 meters. Okay, so it's going to fall 5.05 meters because it's landing, the difference in height is going to be 1 meter. So it's going to be 6.05 meters minus the 1 meter. And so it's going to fall 5.05 meters. Okay, and now I'm going to apply, because it's velocity as it hits the basket 3 meters off the ground. So it's going to fall that far. It will be VF squared equals V naught squared plus 2AD, and that simplifies, and the final velocity is going to be 10 meters per second. The final velocity is going to be 10 meters per second direction. In the downward direction, so it'll be going down 10 meters per second. A little confusing might be here that, well, the basket isn't 1 meter off the ground. Yes, but the difference, you see back at the origin, you see where the original vector is at 40 degrees. And his hands are up. So he's releasing the ball at 2 meters above the ground. So the distance between his hands and the basket is going to be 1 meter. So that's why that looks a little bit confusing. But once you think of it, it's the difference between the release point and the basket. The next problem we're going to do is probably the most confusing of all the problems we have done, with the exception possibly of the basketball problem starring Mubarak. Caitlin is playing tennis against the wall. She hits the tennis ball from a height of 0.5 meters above the ground with a velocity of 20 meters per second at an angle of 15 degrees to the horizontal towards the wall that is 6 meters away. How far off the ground is the ball when it hits the wall? That's the big question. Is the ball still traveling up, or is it on its way down when it hits the wall? That question we're actually going to be able to answer more quickly than question A. Here's the problem set up. I'm going to not spend a lot of time on finding the trigonometric define Vx and Vy using trigonometric quantities. Those should become second nature to you. The 0.5 meters relevant. They kind of talk about that. That's just to try to tell you that it's going to hit it 0.5 meters off the ground. It'll land, we think, 0.5 meters off the ground. It's really an irrelevant number. Y is going to be 0.52 meters per second. You can see as well that Ty 0.52 seconds. And you also can see that when I end up trying to find dy, if I can do it very readily, but I'm going to do it the long way. I'm not going to do it the short way, and there's a reason for that, which I'll explain in a moment. I could do it 5 ty squared, but I won't. There is tx, 1.04 seconds, just to complete it. Really an unnecessary quantity. You don't really need to find tx, but you want to write down everything you know, and then choose from what you have to see if you have enough information to solve the problem. So this is the question. How long is it going to take to go 6 meters? What's going to be the tx at 6 meters? Well, I'm going to say 6 meters divided by 19.3 meters per second, about a third. So the time it takes to go the 6 meters will be a very important time to have. And I see quite readily that it's going to be about a third. Therefore, I know that the ball is going to hit the wall, and the wall will stand probably before Dmax. Dmax is 0.52 seconds. Tx at 6 meters is 0.31 seconds. So I drew the wall in between the origin and dy max at Ty is 0.52 seconds. Now, let's find dy max. I see that I drew in, to make it a little clearer, the distance it's going to, the horizontal distance, 6 meters, and it's going to be 0.31 seconds. Now that I have the horizontal distance, now what I have to do is I want to find two distances. I want to find the vertical distance, dy at dy max, and I also want to find the height, the vertical height at 0.31 seconds. So that's going to be the equation to find dy at dy max, and I simply plug in the values, 0.52 seconds and 5.2 meters per second, and then I crank that out. The negative sign is there because it's going up, and 10 is negative. It should be plus that quantity, but 10 is negative, so that whole second term will become negative. I'm doing it this long way because I'm going to be doing the 0.31 second dy height in the same fashion. And I see dy is going to be 1.35 meters. 1.35 meters, that's going to be dy. So the vertical height. So you see that the height for dy at 0.31 seconds, or at 6 meters, dx at 6 meters, will be less than 1.35 meters. And I'd like to find out precisely the difference between the two heights. So there's the 1.35 meters. Notice here too that on the bottom I wrote the ball would clearly hit the wall on its way up to Dmax. So here is the equation, same equation, but what I'm going to solve for here is the height, the dy at dx at 6 meters. So this is going to be 5.2 meters per second times 0.31 seconds. That's going to be the time it takes to get there, because that's the horizontal distance. The time it takes to go that dx is the same time it's going to go to do the dy. And so the answer will be 1.13 meters. Dy at dx 6 meters will be 1.13 meters. So now what's left to do is I want to show you where that value is, and then put that in the value. There's the dy, it's 1.13. So the ball will clearly hit on its way to Dmax. It'll be 0.22 meters short of dy max. Short of dy max. So fairly sophisticated problem, and you'll do well to review that and keep reviewing it until you can do it in your sleep. Okay, let's do the next one. The last problem is a type 1 projectile motion problem. The Essex County Sheriff is trying to determine the speed of a car that slid off a small bridge on a snowy New England night and landed in a snow pile 4 meters below the level of the road. The tire tracks in the snow show that the car landed 12 meters measured horizontally from the bridge. How fast was the car going when it left the roadway? Well, the bridge is 4 meters tall, so it reached the ground regardless of its horizontal motion in 0.895 seconds. So that's tx, so ty. However, you don't really need ty. The value for Vx, therefore, would be 12 meters. That's the distance. 0.895, which would be Tx. Remember, Ty is equal to Tx, even though we don't need Ty, Tx. So the answer would be 13.41 meters per second. 13.41 second. Many of the problems on the third problem set will have been done on YouTube. I will have done problems in class put them on YouTube. So make sure you look for many of the problems on YouTube. Thanks for listening. Don't forget the quizzes when we return. I hope you will have at least listened to this video and enjoy the rest of your weekend.